Welcome to the third and final video for our Class 22 series of lecture videos. We ended the second video looking at Markovnikov addition of strong mineral acids to alkenes. And by Markovnikov addition, we mean that the alkenes are protonated to give the most stable carbocation intermediate. In this case, where we've got 2-methyl-2-butene, and we're adding HCl, we're going to protonate that alkene in such a way that we form a tertiary carbocation as opposed to a secondary carbocation, because the tertiary carbocation is most stable, and a chloride anion, which is the conjugate base of our acid, is going to substitute into that tertiary cation and give us this 2-chloro-2-methyl-butane as the major product. You can still get hydride shifts or other alkyl shifts that compete with substitution in these types of reactions. So, for example, if we were to treat this alkene with HBr, we would protonate it to give a secondary carbocation as our first intermediate. We could not protonate it to give a primary carbocation because that's too high in energy, not enough hyperconjugation to stabilize it. But once we've generated this secondary carbocation, a lot of things could happen. You could get a 1,2 hydride shift to get to the more stable tertiary carbocation, which could then be substituted. We wouldn't necessarily expect a lot of this product where bromine has substituted that secondary carbon because of these alternative carbocation rearrangements, such as 1,2 hydride shifts. There's no real selectivity for our addition of mineral acids, so if you were to take deuterium chloride and protonate trans 2-butene, you would see both of these stereoisomers plus their enantiomers. So alkene hydration. So this is basically the reverse of E1. All the steps in your E1 mechanism are reversible. So at low temperature, if you put this alkene in with a little catalytic acid, H2SO4, and water, you will add water across that double bond. This is the last step of E1 in reverse. We form the more stable carbocation. Then water substitutes in an SN1-like process, and we deprotonate it. Whose car drives? Well, Le Chatelier, right? So at low temperatures, we're going from the alkene to the alcohol. If we are boiling this, and we've got it under acidic conditions, we might be able to boil the alkene off as it's formed, and then our equilibrium would shift. But in this case, we are adding this alkene to water that's acidified by sulfuric acid at low temperatures, and so we're going to favor the hydration, which is really, like I said, the last step of E1 in reverse, and then SN1. At higher temperature, we get rearrangement. So this is a less stable dialkyl substituted alkene. Here we rearrange to a more stable trialkyl substituted alkene, and we're heating this to distill. So basically we protonate our alkene, we form the more stable tertiary carbocation. Instead of forming the less stable alkene, we're going to move forward by doing our last step of E1 to give us the more stable alkene, and we heat it to distill it, so as it's formed we remove it, and we're not going to go backwards and give ourselves alcohols. So I hope this hasn't been confusing. This is a particularly interesting part or facet of alkene chemistry. Be sure you raise some questions if you're struggling with the ideas in this video during the class, or visit me at office hours, or see your very helpful SI. So good luck with the question, and we'll see you for class 23.